Hello and welcome to a new tutorial in basic electric circuits analysis, and today we talk about series and parallel circuits. So we start with series circuits, and if we look here at this DC circuit, we see these elements R1, R2, R3, three resistors connected in series. And if we look here at the other circuit, we see the three resistors connected in parallel. So virtually we can see that the difference between the series and parallel is the way the resistors are connected. So here, for example, we see that they are connected end to end. So the end of this resistor is connected to the end of this resistor, and then the end of this one is connected to the end of this one, and the end of this one continues in the loop to the end of that one. Whereas in parallel, the two ends or the leads of one resistor are connected to the two ends or the two leads of the other resistor, and so it is across, the connection is across the leads. If we want to see this in an electrical, or if we want to formulate this in an electrical way, we can say that, okay, it seems that in the series circuits that the current flow in all resistors is the same. And that's true. So the current flowing in R1 is the same flowing in R2, flowing in R3. But this is a necessary condition, but not sufficient, because if you look here in this parallel circuit, for example, if we assume that the value of the resistors is equal, so R1 is equal to R2 is equal to R3 is equal to R, then this implies that the total current flowing here will be divided equally among all these three resistors. So the current flow in R1 will be equal to the current flow in R2, equal to the current flow in R3, and still they are in a parallel connection. So the saying that the current flow in all resistors must be the same in order to be series is a necessary condition, but not sufficient. In order to make this complete, we need to say that, okay, we need also that the voltage drop in all individual resistors R1, the voltage drop across R1, plus the voltage drop across R2, plus the voltage drop R3 is equal to the total voltage drop from end to end, to the point 1 to the point 4. And this is actually Kirchhoff voltage law for a loop, for a closed loop here, that the individual voltage drop across the elements is equal to 0. So this one plus this one plus this one is countered by that one. Similarly, if we look here in the parallel circuit, we can say that a necessary condition is that the voltage drop across all resistors must be equal. So the point 2 and the point 3 and point 4 are electrically similar. They have the same potential, the same voltage. And also the point 7 and 6 and 5 are electrically similar. They have the same potential or the same voltage. So we can say that the voltage drop from 2 to 7 across R1 is equal to the voltage drop from from 3 to 6 across R2 is equal to the voltage drop from 4 to 5 across the R3. But this is also, again, a necessary condition, is not sufficient, because if we go back to the series circuit here, if we assume that these resistors are equal, R1 is equal to R2 equal to R3, and we have the same current flow in this circuit, this means that the voltage drop across R1 will be exactly equal to the voltage drop across 2, exactly equal to the voltage drop across R3. So in order to make this complete here, we say that the voltage drop across the parallel resistors must be equal, so VR1 equal VR2 equal VR3, and the total current going to these branches will be divided such that the sum of the current in all resistors equal to the total current going to these branches. And this is actually Kirchhoff current law applied at this node 2 here, where the I total will be divided into IR1, IR2, IR3, and the sum must be equal to the I total. Usually we don't have such simple circuits in our electric circuits. We can have also a combination of series and parallel connection, where we see here that the R2, for example, and R3, they are in parallel together, because these points are electrically similar, have the same potential, so the voltage across R2 is equal to the voltage across R3, and the current going to the I2 is divided such that the sum in R3 and in R2 and R3 is equal to the total coming from this R1. And these two resistors are in series with R1. This is also a simple circuit because we can also have more complex setup where we have different arrangement of resistors in our circuit. So not necessarily series or parallel or series parallel. It could be also star delta, which will be our next topic for the next tutorial, or even something that we cannot identify as series parallel or star delta. It could be also something different. So we start with the resistors, the simplest electric element in our circuits, and resistors in series, and as we can see they are connected end to end. So what we are saying here about series circuits applies to DC circuits and AC circuits, so it doesn't matter, the same analysis applies whether it is DC or AC. So again, we have this resistors connected in series end to end as we visually see it, and we said that the necessary condition is that the current across passing through all elements must be the same, and to be sufficient we need to see that the voltage drop in all elements or all resistors must be equal to the total voltage drop across from end to end, and this makes the thing sufficient. And if we analyze this thing here, the total voltage drop is equal to the sum of the voltage drops here, and since I is similar, so we can take it as a common factor, and then we come to this equation. Now this term here, R1 plus R2 plus Rn, looks like it is the equivalent or the total resistance, hence we come up with the equation that the total resistance of a resistors connected in series would be the sum of the resistors. If you go to inductors, which are present in AC circuits, they have the similar principle like resistors as well. So the current flow must be the same in all inductors. Now the current is a function of time since this is an AC circuit, but it is identical. What about the voltage drop across individual inductors? The sum of the voltage drop across individual inductors must be equal to the total voltage drop from end to end. We recall that the voltage drop across an inductor is given by this formula. It is actually equal to the L, which is the inductance, multiplied by the time derivative of the current passing through the inductor. So we can say that the total voltage drop will be equal to the total inductance multiplied by the current passing in the inductors, and that gives us this equation. And if we look here, if we find the V1 plus V2 until Vn, we come to that this equation here, where we can see that the equivalent inductance is the sum of the inductance. So we can see that resistors and inductors, in order to find the equivalent or the total resistance or inductance, we just add up the resistors or inductance that we have. What about capacitors? Well, capacitors, again, a necessary condition, the current passing through all these capacitors in order to be connected in series must be the same. And again, the current is a function of the time, since this should be a DC circuit in order for the current to pass here. And what about the voltage here? Well, again, the sum of the voltage drop across C1, C2, Cn, if we add it, must be equal to the total voltage drop across all these elements. So the formula to get the voltage drop across a capacitor is given by this equation here. A voltage drop is 1 over the capacitance multiplied by the time integral of the current. And if we start applying this here, we can say that, okay, the total voltage drop here must be 1 over C total, we take this as a C total, multiplied by the time integral of the current passing in all these elements. And this is actually the V1 plus V2 plus until we reach to the Vn. So each one of them, the only difference would be the capacitance of each element here, and the time integral can be taken here as a common factor. And if we compare this part of the equation to that part of the equation, we simply come to the formula that the 1 over C total is actually equal to this thing here. So unlike the capacitors and inductors, the total capacitance, or the reciprocal of the total capacitance, is equal to the sum of the reciprocals of the individual capacitance that we have in our circuit. Next we move to parallel circuits, and here we come back again to resistors. So for parallel circuits, remember we said that the necessary condition is that the voltage drop across the elements must be equal, and there we have it. V1 must be equal to V2, must be equal to Vn, must be equal to V, the total voltage drop. And but this is not sufficient, so in order to be sufficient and complete, we need to say that the current, the sum of the current in all these branches must be equal to the total current. So this gives us the this formula here, that the I total is the sum of the currents here. And if you want to find the current in any branch, I1 is just V1, which is V divided by R1. I2 is just V2, which is also V divided by R2. So since V is a common factor, we take it out and we come to this formula. And if we know that voltage is resistance multiplied by current, so this must be the reciprocal of the total resistance. So we come with this law. Now see that this is exactly how it looks in the capacitors. So the capacitor will take the capacitors, if they are connected in series, they are added in a way like when the resistors are connected in parallel, and vice versa. Next we go to the inductors, and guess what? The inductors will also be the same like resistors. They always follow the same pattern as the resistors. So if the resistors are added in such a way, then the inductors also are added in such a way. So again, the necessary condition here is that the voltage drop across L1 is equal to the voltage drop across L2, equal to the voltage drop across any of the parallel elements here, equal to the total voltage drop. And the current in an inductor. Now, how to find the current in an inductor? Now, remember that we have mentioned that the voltage across an inductor is given by this formula. So how to find the current in an inductor? Well, we just have to move this dt to the other side. The L comes here, 1 over L, and take the integration of both sides, and this gives us this formula here, where the current in an inductor is given by this formula here. Now, if we, the sufficient condition is that the sum of the currents in all these inductors must be equal to the total current coming here. So IL1 plus IL2 plus IL3 plus ILN must be equal to I total. And so the I total is I1 plus I2 plus IN. I1 is given by this formula, where L here is L1, I2, same formula, L is L2. The V is the same since they are in parallel, so we take it as a common factor. So if we compare this thing here with this formula for the I total here, we come to this conclusion that I over L total is 1 over L1 plus 1 over L2 plus etc. 1 over Ln. So inductors in parallel and resistors are parallel, and resistors in parallel are added in a similar way. Now we go to the capacitors, and guess what? The capacitors are always added in a different way. So when they were in series, they were added in such a way as if they are resistors connected in parallel. So now if they are connected in parallel, so simply we can guess that they will be added as if they are resistors connected in series. Now again, the necessary condition in order to be connected in parallel is that the voltage drop across C1 equal to C2 equal to Cn equal to the total voltage. Now, how to find the current inside the capacitor? Now recall that we have said before that the voltage drop across a capacitor is given by this equation, and in order to find the current we can just take the C here multiplied by V and differentiate both sides, so we come to this equation or this formula. So IC1 is just C1 multiplied by this time derivative. The volt will be always the same. IC2 is just C2 multiplied by this time derivative. And the total current passing here must be equal to C total multiplied by the voltage drop. And here we can see it here that the I total is C total multiplied by the voltage, the derivative of the voltage here, which is equal to I1 plus I2 plus I3. This makes it sufficient, the sufficient condition that we mentioned. And if we compare the two sides of the equation, we come to this formula that C total for the capacitors connected in parallel is just simply like resistors connected in series. Now, next, we'd like to make a simple simulation of, just to get a feeling of what is series and what is parallel, and to see, to give some remarks on this setup. So we start with this circuit here, where we have the 9 volt here as a supply voltage. These two resistors, R1 and R2, are obvious that they are in series, and these two resistors, R3 and R4, are obvious that they are in parallel. So to simplify this circuit, we go to this step here where we can add the R1 and R2 since they are in series, and we call this R12, which is actually the sum of R1 plus R2, 2 kilo ohms plus 4 kilo ohms. This is the 6 kilo ohms. And these two resistors, they are connected in parallel. By the way, we have chosen this to be equal, so the result, the sum of these two resistors in parallel would be 3 kilo ohms if we apply the rule that we have. 1 over R total equals 1 over R1 plus 1 over R2. And if the two resistors are equal, then the total resistance is just this, one of the values of the resistors divided by the number of the resistors that we have. So if this is 6 ohm and we have 2, then 6 divided by 2 is 3 kilo ohms. So if we have, for example, multiple resistors here connected in parallel, and all of them are 6 kilo ohms. So we have, for example, 5 resistors, okay, and or let's say 6 resistors, okay. So the total value of these resistors would simply be 6 kilo ohm divided by the number of the resistors that we have, and in the case of there are 6, then it will be 1 kilo ohm. Now, one important remark is that the sum of the resistors connected in parallel here, the sum or the total resistance of two resistors or many resistors connected in parallel must be less than any of the resistors connected in parallel. So this is also gives us a check if our calculation is correct. So if you calculate the total resistance of these two parallel resistors, for example, to be 7 or something greater than any one of these things, then the calculation is wrong. So this is also a check up for us. Now we go further to simplify the circuit further, and now these two resistors looks like in series, so we can add them to get this 9 kilo ohm here. And if we analyze the current passing, the total current passing in this circuit here, it must be the 9 volt here divided by the 9 kilo ohms, which is the 1 milliamp. So 1 milliamp is the total current passing in this circuit. We go a little step backward here. This is the 1 amp, and we can see it here if we put the values here. So this is the total current, the 1 milliamp. Now the 1 milliamp is passing through these two resistors, which we added up in series here, and then goes to the other two resistors which were added here in parallel. And we can guess that the voltage drop across these two resistors here in series will simply be the 1 milliamp multiplied by the 6 kilo ohm, which is like 6 volts. So the volt here must be, since the supply here is 9 and we have a voltage drop of 6, then this must be here 3 volts. The current, again, when you go to the original circuit, was divided, and it was divided equally between the two resistors since they are in parallel and they have equal value. If the value is not equal, then it will be divided in a way inversely proportional to the value of the resistor. So the smaller the resistor is, the more current will pass through it. If we check the voltage, we get the voltage levels that we have mentioned. Now, one last thing here about these circuits. Normally, it is uncommon to see such two resistors in a circuit connected. I mean, we could have just added a 6 kilo ohm in this circuit instead of adding two resistors. And also, we could have added a one resistor here, 3 kilo ohm, instead of adding these two resistors, which is actually more convenient, because then it will be even cheaper. Here I'm using 6 kilo ohm, two resistors, while here I'm just using one resistor, 3 kilo ohm. So it's more convenient actually to use this 3 kilo ohm instead of using two 6 kilo ohms. Well, the reason actually sometimes we need to have some certain value here, which is a non-standard value. So, for example, if I need to have a 3.3 kilo ohm, so and not just 3 kilo ohm, and I don't have 3.3 kilo ohm, so I will think of a certain resistors arranged in a parallel setup in order to give me a total resistance of 3.3 kilo ohm. So this could be also a reason why we use multiple resistors in parallel. And it also applies here for the series resistors. I might not have 2 kilo ohm, I only have I might not have the 6 kilo ohm directly, so I just have 2 and 4 or 3 and 3. So I can use what is available for me, and this will give me the same result. Last thing here is about the parallel connection. Usually the trade-off, if we need our loads to have a fixed or a constant voltage, then we need to connect them in parallel. So any resistor connected or any load connected in parallel would get the same voltage. And if we need to have them having the same current, we need to connect them in series. And so if we think in our house, for example, where we see the sockets, the electric sockets in our house, so for all the appliances that we are using, we need to get a constant or a constant voltage for the devices, whether it is 220 or 110. So this means that all the connections in the house, for example, are connected in parallel, so that this will ensure that we get the same voltage for all the appliances. Now, the more appliances we add in parallel, the less the total resistance is, and we can see this here in this thing here. So this was 6 kilo ohm. We added another one 6 kilo ohm, so the total value dropped to the half. Now, if we add another one and another one and another one, the whole thing will continue to drop, and this will withdraw more current from our source voltage. So the minimum or the maximum that we can add is limited by the current that is allowed to pass in from our supply to our loads. And otherwise we can get we can almost come to a very high current consumption here if we continue to add more resistors in parallel here. Now, this was the basics of series and parallel connection. In next tutorial we'll discuss the star delta or delta star connection, which is another common form of circuit setup, and the analysis, and we will go for more complicated or more complex analysis for circuits. So until then, thank you.